we will discuss one important result, which is Euler's polyhedron formula. Euler's polyhedron formula. The statement of this theorem is, suppose G is a connected plane graph. Suppose G is a connected plane graph with P vertices, Q edges and R faces. Then P minus Q plus R is equal to 2. This result definitely holds. So this is the statement of the Euler's polyhedron formula. If G is a connected plane graph with P vertices, Q edges and R faces, then P minus Q plus R is equal to 2. Let us verify this result with this example. So how many vertices are there in this graph? 1, 2, 3, 4, 5, 6, 7. Now number of edges: 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 edges. Am I right? Next, faces. There are 3 interior faces and 1 exterior face, totally 4 faces. Now if I substitute the values of P, Q, R in this result or equation, what happens? Let us see. 7 minus 9 plus 4, it must be equal to, say it is 11 minus 9, which is equal to 2. So the result holds for this graph. So therefore the statement is 100% true. I written P, it should be Q. So in this graph, P equal to 7, Q equal to 9 and R equal to 4. If we substitute the values of P, Q, R in this equation, definitely it satisfies. So therefore the result is 100% true. Now we try to prove this result. How to prove the result? So we try to prove this result by using mathematical induction on Q. Now we try to prove this result. Okay. So how to prove this result? By using mathematical induction on Q. Suppose Q equal to 0. Already we have considered a connected graph. When Q is 0, then what kind of graph we will get? We will get only a graph having only one vertex. Definitely, because it is a connected graph and Q is 0. Obviously this will be the graph. So in this graph, P is 1 and R only one face, that is exterior face 1. So therefore when Q is 0, P is 1, R is 1. So if you substitute these values in this equation, P minus Q plus R equal to 2, definitely holds. So therefore the result is true in case of Q equal to 0. So now we consider Q, which is, suppose we try to consider the case 2. Suppose Q is greater than or equal to 3. Okay. Now we consider 2 cases on this. So now I have considered Q greater than 2, so sorry for that. Case 2, what we will do, we will assume the result is true for fewer than Q edges. This is the assumption. First, already we have proved the result is true for Q equal to 0. Now we have assumed the assumption is that the result is true for fewer than q edges, means less than q edges, where q is greater than 0. In this we will consider two subcases. A. Suppose G is a tree. Suppose G is a tree. What happens? If G is a tree, already we know the definition of a tree, which is connected acyclic graph. It implies, by one of the previous result, if G is a tree with P vertices and Q edges, we have got one result. The result is Q is equal to P minus 1, or you can say P equal to Q plus 1. This is a result, one of the results in the tree topic, because G is a tree with P vertices and Q edges. Definitely P equal to Q plus 1. And how many faces will be there in the tree? Only one face, because there is no cycle at all. So only one face. So therefore, if you substitute the value of P and R in the equation, what happens? P minus Q plus R equal to 2. That was the result. Instead of P, what I should do? P minus Q plus R is equal to 2. This was the result. Now we will substitute. So if you substitute, what happens? P minus Q, you can use P minus 1, plus R, R is 1, it must be 2. So therefore P gets cancelled, minus 1 plus 1 is equal to 2. So therefore the result holds in this case also. So now we consider another case. Suppose G is not a tree. Suppose G is not a tree. It implies G contains a cycle. Let C be the cycle of the graph G, and E be an edge on this cycle C. If I delete this edge on C, what happens? Then the graph G minus E has how many vertices? P vertices, because we are not deleting any vertex. And how many edges? Q minus 1 edges, 1 edges. And how many faces? Earlier it has got R faces. Now from C we have reduced or deleted 1 edge. It implies 1 face is reduced. So therefore it has got R minus 1 faces. So by inductive hypothesis, so this graph has fewer than Q edges. So therefore by inductive hypothesis, it must satisfy P minus Q plus R equal to 2. That is P minus Q. Q is Q minus 1 plus R is R minus 1 equal to 2. This is true by inductive hypothesis, because we have assumed it is true for fewer than Q edges. Now if I simplify this, it is true. So therefore P minus Q plus R is equal to 2. It is true. Hence the result is true for all Q in this case also. So now we will discuss another concept of planar graph called maximal planar graph. A planar graph is said to be maximal planar graph if no edge can be added without losing planarity. So it is not possible to add one more edge. If you add one more edge to that planar graph, it will not be a planar graph. So that graph is called a maximal planar graph. For example, this is a maximal planar graph. Now you cannot add one more edge. We will consider one more planar graph. This is also maximal planar graph. Now you cannot add one more edge. If you add, it will not be a planar graph. Now we consider another example. Now, is it a maximal planar graph? Is a question. Okay. Still, you can add one more edge. Still, it is planar graph. Is it possible to add one more edge? See, earlier it was planar. Even though we can add one more edge, even though it is planar. Now, is it possible to add one more edge between the two non-adjacent vertices? Even if we try to add these two non-adjacent vertices, what happens? It violates the planarity condition. Then another possibility, if we add these two vertices, what happens? Even though it violates the planarity. So therefore, this is a maximal planar graph. Now what is the observation in the maximal planar graph? Very simple observation. If you observe the maximal planar graph which is embedded on the plane graph of the maximal planar graph, if you observe, every region is a triangle. See, this is a region which is a triangle. See, every region of the maximal planar graph is a triangle. Even the exterior region is also a triangle, bounded by 3 edges. See, this is also bounded by 3 edges, 3 edges, 3 edges, 3 edges. Every interior face is bounded by 3 edges. Even the exterior face, 1, 2, 3. So such graphs are called maximal planar graph. We try to prove another theorem. Suppose G is a connected planar graph. Connected planar graph with P vertices, Q edges and R faces. Then there are two results. One is Q is greater than or equal to 3 by 2 R, and the second one is Q is less than or equal to 3P minus 6. We try to prove these two results. Proof. Suppose G is a connected plane graph. Okay, planar graph of course. Let G1 be a connected plane graph of G. Plane graph of G. Then what is the observation? The observation is every edge of G is exactly on two faces. For example, if I consider this as an example, let us think of this. This is a plane graph. Every edge is on exactly two faces. Every edge is exactly on two faces. It implies, what it implies? 2Q, and how about the face? Every face is bounded by at least 3 edges. At least 3 edges. So therefore 2q is greater than or equal to 3r, which implies q is greater than or equal to 3 by 2r.